This is Learning Assessment Problem 1115. The problem-solving strategy here is that of three-phase balanced AC power circuits. For the circuit, we are referred to example 1110 and figure 1121. In the problem statement, we are to determine the value of the capacitors C in this balanced load system such that the load power factor is improved from 0.78 to 0.9 lagging. Some information given about the system is that we have a 34.5 kilovolt line-to-line voltage. The frequency is 60 hertz. The total apparent power absorbed in the balanced load is 24 megavolt amperes. Let's consider some currents in this system. We'll call this current e11 flowing into the balanced load. We'll have a capacitive current when we install the capacitors I sub C, and then the current which flows from the source after installing the capacitor, we'll call that il2. So we'll do the analysis of this problem by working with the expressions for complex power and apparent power in the system. We'll assume that we'll work with the A phase of this three-phase system, and the magnitude of that voltage will equal V line divided by the square root of 3, which is 34.5 kilovolts divided by the square root of 3, and that's equal to 19.92 kilovolts for the magnitude of the phase voltage. For the general expression for V sub A and phase voltage, let's assume that it is a magnitude V sub M at an angle theta sub V. Then the current IL1, which flows from the source, will be of the form an IL1 magnitude at an angle of this theta sub V minus theta L1, where theta L1 is equal to the inverse cosine of the power factor 1, which is the inverse cosine of 0.78, which is equal to 38.74 degrees. This angle theta L1 is the angle by which the current in the load lags the applied voltage VAN. Then for the complex power, as L1, we'll designate that as a vector quantity or complex quantity, is equal to VAN phasor times the complex conjugate of IL1 phasor, and this will equal, in terms of our labeled values, Vm times IL1 magnitude at an angle of theta L1. Now the magnitude of this complex power per phase is equal to the 24 megavolt amperes given in the load statement divided by the three phases, and that's equal to 8 megavolt amperes per phase. So now we can write the expression for this SL1 complex power per phase is equal to 8 at an angle 38.74 degrees megavolt amperes per phase. In polar form, SL1 per phase is equal to 6.24 plus J 5.006 megavolt amperes. With the capacitors inserted in the system, we'll have that the theta L2 angle is equal to the inverse cosine of the new power factor 0.9, which is equal to 25.84 degrees. After adding the capacitors to improve the power factor, we'll have a new expression for our complex power SL2 per phase is equal to 6.24, the original real power dissipated in the load, that remains unchanged, plus J 6.24 divided by this cosine of the 25.84 degrees, and then multiplied by the sine of that same angle, 25.84 degrees. This is equal to 6.24 plus j 6.24 tangent of 25.84 degrees. And finally, we have the new complex power expression is 6.24 plus j 3.022, and that's megavolt amperes. That new complex power, SL2P, is equal to the complex power, or the quadrature power, supplied by the capacitor, S capacitor, plus the original expression for the complex power, SL1P. And the reactive power supplied by the capacitor will equal SL2P minus SL1P. So the reactive power supplied by the capacitor is equal to J 3.022 minus 5.006 megavolt amperes, and this is equal to minus J 1.984, and since that's reactive power, that would be megavars. The significance of the minus sign here is that the capacitor supplies reactive power, whereas an inductive load will absorb reactive power. In terms of the capacitor, the reactive power is equal to minus j omega c Vm squared, and that's equal to the value we just obtained above, 1.984 megavars. So the minus j's will cancel out, and we can solve this expression for the capacitance is equal to 1.984 megavars divided by omega Vm squared. It's equal to 1.984 times 10 to the 6th volt ampere reactive divided by 2 pi times 60 hertz for the radiant frequency, and times 1.992 times 10 to the 4th volts squared, or the capacitive value is equal to 13.26 microfarads, which would have to be added to each phase to produce the new power factor value.